All right, today we're going to be looking at section 3.2. This is the derivative as a function, and as we go into it, we've been talking about finding the derivative at a point and what the derivative is, the slope of a function at a point, but now we're going to be looking at the derivative as a function. So we're going to come up with a function that's going to give us a derivative, and we can find the slope along our original curve as we move. So here they're kind of giving you a visual of a general graph, and the slope as we move along that line is changing. It's positive on this side, then it's 0, and then it goes negative. So as we work toward this definition, which we call f prime, we use f prime and we define it as the limit of f of a plus h minus f of a divided by h as h goes to 0. So this will find the derivative at the point a. But in general, we can find a function, and so here's the definition of a derivative as a function. We just do f of x plus h minus f of x all divided by h, and this is as h goes to 0. And this is if the derivative exists, we say it's differentiable, and if it is differentiable at every point in the open interval, we say that f is differentiable on I. So that's going to be very important later, noting that f is differentiable on every point in some open interval. So here they kind of go through and just show you an example computing a derivative using the definition. And then here you can kind of see just the multiple changes as you find that derivative and you plug in different values of x, you're going to get different slope values. It's changing all along that line. So this kind of goes into a little bit more of the background and how you derive it, and it goes into different forms, different ways that we represent derivative notation. So you have the f prime of x, which is one of the most common ones. You also might see dy dx. These are also common, but these are some alternative ways of writing derivative. You might say df dx, so derivative of the function f with respect to x. They might write it d dx, and then of f of x. You might see this notation, and then you might see y prime of x. So these below are the derivative evaluated at some value a, and these are also some methods that you will see as well. And they just all mean derivative of y with respect to x. So here's some more calculations, just showing you how to compute derivative with different functions. Then we want to look at the graph of a derivative. So here they're just saying we want to sketch the graph of a derivative, and they're kind of explaining what's going on with these segments. So this black line is your original graph, and we talked about the derivative being the slope. So if we look at the slope and you look at the slope of this line is -1, and they're kind of explaining this here. And so the derivative, which is the red graph, is just a horizontal line at -1. And then there's a change. It goes from being negative and then positive all of a sudden. So this next section looks like a +1. So we have a horizontal line at +1, and then we have another change. So in the reading, it kind of explains the abrupt change, and it says it's undefined, which we'll talk about that a little bit later in this section. And then it goes over sketching the graph of derivative. So we kind of see what's going on when we're less than this point, greater than this point, and so forth and so on. One of the things they do make note of is that the points where you have a 0 slope, these will be the maximum or minimum points, and they're kind of explaining that here. So when you see a max or minimum or flat point, that lets you know the slope is going to be 0, and that means the derivative would be 0 at those points. And then based on the slope of the line, once we input those zeros, we start talking about, well, what's going on? Well, it has a positive slope left of -3, and then at 3 we reach 0. So that means that the graph is above the x-axis, okay, and they kind of draw it here. You see the red graph. So positive means we're above the x-axis when we look at the derivative, and then it's going down till we hit 0. And then the next slope is negative. Negative means you're below the x-axis. And then a positive slope would mean you're above the x-axis again, and then a negative slope means you go below. So they kind of explain a lot of that in the reading, and then also let you know how to do it when you have asymptotes. So this is all going to be good to read over. Again, they're just kind of showing you what's going on. Negative slope is going to be below the x-axis, negative slope below the x-axis, and then a flat point, minimum, maximum, you got 0. Positive slope, it goes back above the x-axis, and then negative slope below the x-axis. Now we talk about continuity and the relationship, some of the stuff that we've seen before. It says if it's differentiable, it implies that it's continuous. So if you know that a function is differentiable at a, that means it's also continuous. And then we kind of go through the definition, just kind of reiterating some of those points and things we've talked about. Then it also tells you in the alternate version, if it's not continuous, that means it's not differentiable. So it says if f is not continuous at a, then it's not differentiable. And then we kind of go into details. If f is continuous at a point, it's not necessarily differentiable just because it's continuous. And it tells you to consider the figure below, it has a corner point. If you ignore that corner point, it looks like this whole thing is continuous. But we cannot find a derivative of a corner point. And that's kind of why we saw those breaks and jumps in the previous graph. If I go back a few pages, this graph right here, when we hit these corner points, you saw breaks and jumps. That's because it's not differentiable at a corner point. Okay, so this reading kind of just explains those different things. If you've taken some other courses, you might have talked about logic and contrapositive statements. These are just two ways of saying the same thing. If it's differentiable everywhere, it's continuous. And if it's not differentiable everywhere, then it's not continuous. It kind of explains that in the sideline. And then they give you some notes to take away. So how do you know if a function is not differentiable at a point? These are some of the conditions that you will notice. F is not continuous at a, okay, so like you have a hole, a break, or jump. If f has a corner point, sort of like this diagram here, and then if f has a vertical tangent line, like this one. So if you got some shape like this, cube root of x, that would not be differentiable there. So any of those you notice, that lets you know the function is not differentiable. And then that would kind of wrap up the section. They just give you a few more examples and showing you how to use the function to draw the derivative of a graph. And just remember, the slope tells you the position of the derivative. If it's just a linear line, it's going to be at 1 positive. If it's negative slope, it's going to be below the x-axis until you hit some asymptote, and then you have positive, and then it goes to negative. So let's jump over to my MATLAB and do some problems.